great to be here. Every time I come to Waterloo, I haven't been here in a while, but every time I come here, I feel like I'm coming home. So it's actually a privilege to be here. I want to start my talk with a question for you, just to get you thinking. And you know, the question that I have, you don't have to know the answer, but it'd be interesting to actually see your opinions or hear your opinions about it. So DRAM. DRAM is the technology that we use to make memory. It's very popular. You know, most of the memory in the world uses DRAM. And there are 3 companies in the world that make 95% of the DRAM out there. And I can name these companies. Samsung is one of them, SK Hynix, and Micron. These are 3 companies that make 95% of the DRAM. And they sell this DRAM to markets. What market do you think consumes most of the DRAM in the world? Which market demands has the largest demand of the DRAM out there? You know, as this question, keep in mind that, you know, the whole work here is sort of from the perspective of a cloud provider, right? So it's sort of these data centers, lots of data centers with a lot of servers, with a lot of memory. Who is the largest consumer of DRAM? Who purchases most of the DRAM in the world? What do you think? That's right. So this is actually, to me, I always am very sort of, you know, it's shocking because I always think, oh, the cloud has a lot of DRAM out there, and Microsoft is one of the large cloud vendors, but not just Microsoft, Amazon, Google, and so on and so forth. But they are nothing compared to the smartphone market. The smartphone market actually consumes most of the DRAM. It's sort of interesting. I always find that very fascinating. Okay, so let me introduce a little bit the people who worked on this project. This work was done at Microsoft Research, MSR, in Redmond. And we had, last year, we had 2 interns, Jeremy and Minesh, who helped get this project off the ground. They are students from Onur Mutlu's group at ETH. Lucian came after earlier this year and actually built on top of this work and produced a number of really interesting results. And the results I'm going to present today are mostly based from you know, sort of obtained by Lucian's work. Lily was another student we had over the summer. She worked on a different project, but she actually ran some experiments that actually helped clarify some of the findings here. And then Alec Wollman is a longtime collaborator. He helped guide the work and provided feedback. Okay? I want to tell you, feel free to interrupt me at all points in time. My goal here is not to go over my slides and make sure I tell you everything I wanted to tell you, and so on and so forth. My goal is for you to leave with something that you actually understand and take away. So if it's something that's unclear to you, that's a sign that I did not do a good job presenting it to you. So stop me and ask questions, okay? In 2014, a study of 129 DDR3 DIMMs showed that aggressive DRAM accesses can cause bits to flip. So you have to aggressively access DRAM, and you're going to cause bits that you actually don't control, that you have not even accessed, to flip in your memory. And they show that this problem is prevalent. It affected something like 80% of the 129 DDR3 DIMMs that they tested. And this is a really bad problem, the fact that you flip bits in memory. It's bad because it violates a very simple basic assumption that software makes about hardware. And that assumption is that the value I read at a particular memory location is the same value that I last wrote, that was last written to that memory location. And the moment this assumption is not true anymore, all software systems, especially with respect to security, they crumble. And this affects the security of your system and the privacy of your system. And cloud providers care about security a lot, and they care about privacy even more. It's very difficult to run a cloud business when your customers do not trust that their data is safe inside of their data centers with respect to privacy. And indeed, and they coined this term called DRAM disturbance errors. This was sort of the term they coined. And over the next 5 years, there was a plethora of papers published by the security community, all exploiting this problem to attack their favorite system. The goal of this slide is not to go over these papers or to read their titles and think about them. This is only a small subset of the many, many, many papers that we actually have on Rowhammer. And what these papers do, they all show that this particular problem, the DRAM disturbance error problem, I can use it to exploit pretty much any software system I can think of. I can exploit operating systems, virtual machines, hypervisors, browsers, network protocols, SSH, you name your favorite security systems, I can exploit it using this problem. The other thing they showed is that DRAM disturbance errors is not a problem that affects DDR3 only. It affects all DRAM. DDR3, DDR4, low power DDR, DRAM that's equipped with error correction, ECC-equipped DRAM. Rowhammer is a problem that affects all types of DRAM. There is actually a cool paper here that's very recent that appears at SMP Oakland next year, where people have shown that you can even read memory with Rowhammer, with this problem. And the way you do that is you sort of look at how bits flip in the memory, and by looking at where the bits flipped, you can infer, you can guess the value of other bits that you haven't flipped. And that allows you to read memory, and it's called RAM bleed. Now, to cause these DRAM disturbance errors, an attacker needs to hammer one or several rows inside of DRAM to access them frequently, and that's why the attack is called Rowhammer, because we hammer rows. Well, people are fascinated about Rowhammer, and the media did not hesitate to capitalize on this fascination. While there are many research papers on Rowhammer, there are even more articles explaining in layman terms what Rowhammer is and predicting many doomsday scenarios. Each time Rowhammer made the news, the memory vendors did not hesitate to also make all sorts of claims, okay? And their claims were different. Most of them were ridiculous, but they all followed the same template. And that template is, oh yes, we knew about Rowhammer. Rowhammer is a problem that affects the older type of memory, but the one that we're currently selling right now is not a problem for this memory. Trust us, Okay, so don't worry about Rowhammer, just buy our memory, it's fine. And what I have on this slide is two quotes from major memory vendors that were made in 2015. And those quotes were after the first paper came out, and these basically say, yes, Rowhammer is a problem that affects DDR3, but DDR4 is Rowhammer free. Don't worry about Rowhammer and DDR4. And this is false, demonstratively false, these statements, okay? So, and now there are other claims that they make about sort of newer types of memory. And once DDR4 was shown that actually you can mount Rowhammer on it, then yes, but if you put ECC on your DDR4, then it's safe. And we know that's also not true. I want to reemphasize this point that Rowhammer affects all types of DRAM. Okay, it's sort of fundamental to how DRAM works. Now, this avalanche of papers and news articles made multi-tenant cloud vendors very nervous about Rowhammer. And they're nervous for two reasons. Reason number one is that Rowhammer is a very easy attack to mount in practice. All you have to do is you buy a VM in the cloud, which is very easy to do, and you start hammering memory. And if you're successful, you're going to actually cause that server to reboot because you're actually going to corrupt some state in memory. Or even if you're more successful, you're going to compromise that server. And both problems, both the compromise problem and the reboot problems, are problems that the cloud providers are very nervous about. They don't want that to happen in their cloud. The second problem has to do with the media articles. And the media articles portray the cloud as defenseless in the face of these attacks. And that is true. There is no software patch we can install on our servers to basically say, oh, these servers are now Rowhammer free. It's sort of fundamental to how the hardware works. Cloud providers are very nervous when they see all these sort of news articles showing the cloud is actually defenseless. Here's a new attack, and there's nothing you can do to stop it. However, the more interesting part to me as a researcher is that cloud providers have a very difficult time understanding whether their memory is resilient or not to the problem of Rowhammer. Despite this overwhelming amount of papers on Rowhammer, what these papers show are what's called proofs of concept, or proof of concept attacks, where you take a particular software and hardware configuration and you line everything up the proper way, and you're going to cause a particular important bit that you care about to flip, and when that happens, you can compromise the system. It's very difficult to understand how, or it's hard to understand how difficult it is to generalize this proof of concept. Well, I can mount this attack in the lab. Can I mount it in a fleet of servers running inside of the data center? How difficult is that? That's actually a hard question to answer, and that's one of the questions we're going after. There are also Rowhammer skeptics. I have talked to people who thought that maybe Rowhammer is just a made-up problem, and it's not a made-up problem. Rowhammer is not, it exists. But the good question they're asking, and it's a good question to actually think about, if Rowhammer, if the threat of Rowhammer is so imminent, why are there no attacks in practice and, in the wild? And to my knowledge, there is no public information about the Rowhammer attack being mounted in the wild, okay? So why is that? And that's the goal of our work. So in this talk, we're going to develop an end-to-end methodology. And our goal is to develop this methodology that can test any cloud server whether it's susceptible to Rowhammer. And using our methodology, we developed a test for the cloud server based on Intel Skylake. This is a class of servers that, for a class of servers from a major cloud provider. You can probably take a guess of what that major cloud provider is. And they're based on Intel Skylake. Skylake is a major Intel architecture. Pretty much all servers rolled out in data centers today are based on Skylake, and that's, I can't really verify this claim that I'm making, but I suspect all major cloud vendors today are all Skylake in their data centers. The next major Intel architecture is called Ice Lake. Intel has announced it, but you can't really buy CPUs with Ice Lake yet. Okay, so I told you about Rowhammer. This is an outline for my talk. The goal of this slide is not for me to go and tell you about the outline. The goal is to sort of, every section of my talk, I want to come back to this outline, give you a chance to sort of take a step back. So I told you about the motivation of the work we do. The next thing I'm going to talk about is background on DRAM and Rowhammer. Now, this background, it's a fairly long part of the talk, but it's a necessary part because in the absence of understanding how DRAM works or Rowhammer, it's very difficult to really understand what is this work about. And I always found that the audiences really like this part of the talk quite a bit, including people who work on DRAM. They felt like, this is an interesting sort of important point. Yes, please.
So what do you care about Skylake?
Oh, so why is Skylake? It's because in order to attack it, you need to execute instructions. And the side effects of executing those instructions cause bits to flip. And when you execute these instructions, you're subject to the underlying architecture that you use. And I'm going to show you sort of things. So for example, Skylake has new instructions that you can use to flush caches that did not exist before. And it turns out that those instructions are very handy to actually hammer your memory. So that's one reason for that. Great question. OK, this part of the talk is bottom-up. Bottom-up presentations are confusing because it's not clear why you're telling me why I'm telling you what I'm telling you, but they're useful to understand. Okay, so this is more like a lecture, this part of the talk. Then I'm going to go top-down after this. What you see on this slide is a DIMM. DIMM is the way in which DRAM sits on your desktops or on your servers. And the DIMM refers to this PCB. And on the PCB, I have chips. Okay? And there are two chips in the middle called an SPD and an RCD, and I can tell you what they are, but it's not important for this talk, so I'm not going to actually spend time telling you. If you're interested, talk to me afterwards. They're not important for the most part with respect to Rowhammer, although that's a hard statement to defend. But the chips that I care about are these data chips. The DIMM here is a 32 gigabyte DIMM, and each chip here is a 1 gigabyte, stores 1 gigabyte of data. And if I count it, I have 9 chips on a row here. And this DIMM has 4 rows. It has 1 row at the bottom, 1 row at the top, 2 rows. And there are 2 rows on the other side of the DIMM that you can see in this picture. So there are 4 rows times 9 chips. That's 36 chips. Each chip is 1 gigabyte. That's 36 gigabytes. And I just told you this is a 32 gigabyte DIMM. So what's going on? Why do we store 36 gigabytes? Well, it's because this actually supports ECC. And by the way, this is a quick way for you to test, to check whether your memory supports ECC or not. What you do is you count the number of chips on the DIMM. And if it's a power of 2, it doesn't support ECC. But if it's a power of 2 plus some k here is 4, then chances are it supports ECC. Okay? And the fact that it supports ECC doesn't mean that you run ECC. You have to enable ECC in the BIOS, because the memory controller needs to understand ECC too and talk to the DIMM appropriately. OK, so that's a DIMM. Now, again, bottom up. This is one DRAM cell. And this is the circuitry of a cell, vastly simplified. And DRAM uses capacitors to store data. And a capacitor, the way to think about it is a capacitor can be charged or not charged. And if it's charged, then it stores data. If it's not charged, it doesn't store data. And in this picture, I'm saying, oh, if the capacitor is charged, that means that the cell has 1 stored in it. But that's not necessarily true. You can also use an encoding scheme where a charged capacitor corresponds to a value of 0, and a discharged capacitor corresponds to a value of 1. So it's up to the memory how it encodes the data. But in this picture, I'm going to assume that the charged capacitor corresponds to a value of 1. And this is a schematic. And to read this memory cell, what I do is I apply current through a select line, and that has a transistor there. The fact that I have only 1 transistor per cell, it's good because it means that to produce my cell is cheap and inexpensive, and that's why one of the main reasons why DRAM is very popular is because it's cheap to manufacture, or cheaper to manufacture. So when I put current through that line, I close the transistor, and I close this circuit, and that causes the capacitor to sort of discharge, and that's how I read my data. What's important here is that when I read the value 1 from the capacitor becomes discharged, so I have to write back that value if I want to maintain the value in the future. And a lot of time when I present this, people say, oh, I knew that. I knew memory DRAM refreshes itself. So that's refresh. This is not refresh. This is a separate problem. This is not refresh. This is the fact that when I read memory, I have to write it back to DRAM in order for it to actually be there next time I want to read it. OK. I'm taking a step out. This is a bank. A bank is basically an array of rows and columns. This is a vastly simplified picture because I have many, many, many columns and many, many different rows, and a row buffer. In order to read data, and the data is stored in the bank in this array, but to read it, I have to move data into the row buffer. I have to copy data into the row buffer. So let's assume I want to read row 2, and those are the values of row 2. The way I do that, I put current through all my columns, and then I put current through this row line, row number 2. And that's how I close the circuit with the row buffer, and that's how all these capacitors sort of leak their charge into the row buffer. But then what I have to do is I have to write back the row buffer into the data to make sure it's there. All I did now, I just copied the data from the array into the row buffer. I haven't yet read it. How do I read the data? OK. Let's take a step back. On the right-hand side, I have the bank I was showing you before. Because I don't have enough space, I only show you 4 columns rather than 7. Don't worry about that. On the left-hand side, I have a very simplified picture of a CPU. A CPU is just a bunch of cores. Each core has local caches, an L1 cache and an L2 cache. And they all share an L3 cache. And CPUs have 1 or more memory controllers. And that's how they talk to the memory through the memory controller. And the CPU executes instructions. And let's say they execute a load instruction, which is how you read data. So you execute load A, and you first look into the caches. If that physical address appears in your caches, you can serve it from there. In this diagram, I'm assuming it's not. So eventually, that instruction sort of lands into the memory controller. So the memory controller says, I have to go to memory to read my data. The memory controller now maps that physical address A to a set of DIMMs, channels, ranks, banks, rows, and columns. And here, I'm assuming that A maps to this particular bank to row 1, column 1. OK, I'm making that assumption. Who maintains this map? The memory controller. Who makes the memory controller? Intel, in our case, or AMD, or ARM. How are these maps? Where do these maps are published? They're not published anywhere. Who knows them? You reverse engineer. There is no document you can read about these maps. People try to reverse engineer these maps all the time. So the memory controller now says, oh, I need to activate row 1. So what I'm going to do, I'm going to put current through the columns and through row 1. I move the data to the row buffer. Then I write it back. Right? Now I put the data in the row buffer. And only now I can read column 1. So I'm going to read column 1. And column 1 corresponds to value 0. So the memory controller now returns back to the CPU the value of A. And the CPU can continue computation. But what's interesting here is that the memory controller is not done with this thing. The reason why we're not done is because we still have data in the row buffer. And we might need to clear it if you want to move data later on. And also there is current through this circuit that is not back to the original thing, which I'm not showing here through the animation. So there is a third command that the memory controller needs to issue called precharge, which clears this row buffer and changes the circuit back to the original state. So now I can activate a different row if I want to. Any questions? I hope this is pretty clear. I cannot make this simpler than this. Yes, Ian?
So when you read memory, you show reading 1 bit. But in reality, presumably it doesn't read 1 bit at a time.
So that,
how much memory is read at a time?
right. So this, the width of that, oops, sorry, that's great. The width of this channel is 64 bits. And, sorry, actually, that's, okay. So you read 64 bits over this channel, okay? And when you read 64 bits, that corresponds to 64. So I'm only showing 1 bit here. A row is 64 kilobits, so 65,536 bits in length. When I move a row here, when I copy a row into the row buffer, I read 64 bits of it. And then if I want to read a different 64 bits, I don't pre-charge back the row. I keep the row in the row buffer because that's cheaper for me. And there's a lot of sort of dances that memory controllers make to make sure that when you actually read memory, because most memory you read is actually linear, is done in such a way that you tend to hit the row buffer as much as possible because that's better for your performance. Okay? The 65,000 bits, this is for DDR4 memory. Everything I'm talking about today is about DDR4, which is the one that people use today. Okay. Now, I haven't told you anything about refreshes. So let me tell you a little bit about refreshes. Well, for DRAM, we use capacitors, and capacitors sort of lose charge over time because that's how capacitors work. That's physics. So the memory is built in such a way that it has to be refreshed periodically. And people have a convention where the memory vendors say, I'm going to build my memory in such a way that I'm going to guarantee you that it's not going to lose its contents within 64 milliseconds. But the system, the hardware, needs to refresh the memory at least once every 64 milliseconds. And if I do that, then everything is fine. And how is that done? Where the memory controller decides when it's time to refresh, and it sends a refresh command. And here, sort of, you might think, oh, because the memory controller sends a refresh command, then the chip is going to go, the bank is going to go refresh all its rows. No, that's not how it works. This stuff is super complicated. So let me tell you why that's not how it works. When the memory refreshes itself, the bank is unavailable. You cannot do any useful computation. You cannot read data or write data to it. And that will take a long time to refresh the whole bank. So what the engineers did, they said, oh, we're going to, instead, rather than sending one refresh every 64 milliseconds, every 64 milliseconds, we're going to send 8,000 refreshes. And the job of the bank is to only refresh a portion of the rows, 1/8,000 of its bank size. And if you do that, then every 64 milliseconds, every row is refreshed at least once. And by chopping the refreshes finely, this means that the bank never becomes unresponsive for a long period of time. Every time a refresh command is sent, the bank becomes unresponsive, but just for enough time to refresh something like 32 rows, something like that. Okay? Yeah?
Sorry, you probably said it and I missed it, but what does refresh involve?
No, I did not say what refresh involves. So refresh, so when the memory receives the refresh command, what does it do? It doesn't do anything special. What it does, it basically activates the row, puts it in the row buffer, and writes it back. That's all it does. Okay, so it's basically, that's all the memory knows what to do. Activate the row, put in the row buffer, write it back. So that's a refresh. That's, in fact, the write back is the thing that you refresh the capacitors back to.
So in theory, if you had capacitors that have less leakage, you can delay the refresh.
You could. So you could build memory where your capacitors actually are going to hold charge for 120 milliseconds, and then you change the protocol. But the convention, the people who build this hardware are memory companies. The people who build this hardware are the Intels of the world, and they need a convention. So the convention is, you build my memory every 64 milliseconds, and I'm going to guarantee I'm going to issue that refresh to you every 64. You have to 8,000 refreshes every 64 milliseconds. That's the convention. Okay? Now, Rowhammer. So for Rowhammer, I'm executing a set of instructions in a loop. And what I'm doing doing, I'm executing two reads, load A and load B, and I chose A and B in such a way that they correspond to row 1 and row 3. And when I'm executing this in a loop, because I want to hammer memory, if I don't have cache flushes, I read the memory once, then I store it in the caches, and then I'm going to read the caches only. So to hammer the memory, I need a way to flush my caches. And there are different techniques you can use to flush your caches. So I can flush my caches in different ways. I can build cache eviction sets. I can use different instructions. These are CL flush instructions are the instructions that many Intel CPUs support, and that's a favorite way of flushing my cache. I flush A and B. I'll come back to the flush instruction that Skylake supports that's different in just a moment.
Caches are impervious to similar attacks?
Yeah, caches don't use DRAM. They use better memory that we don't know how to Rowhammer it. There might be some way to flip bits in the caches, but we don't know how to do that yet. So if I do that, what I'm going to do is I'm going to alternate successively rows 1 and row 3, activating them. And when I put current through those rows, there is an electromagnetic effect, coupling effect, that some of that current leaks on adjacent rows. And that caused the capacitors on row number 2 in this example to discharge faster than they're supposed to. And that's how they flip bits. And what I do here is what's called a double-sided Rowhammer, where my victim row is row number 2, and I'm hammering it both on row 1 and on row 3, and that's the worst damage I can do to it. I can sort of discharge the capacitors faster that way. And I have another animation to show that where I'm going to flip bit 0 here, because that's the bit that's flipped. So I'm alternating row 1 and row 3, and if I do that, flip bit number 1, column number 3 is going to flip its bit. Yes? So it depends on what encoding scheme the memory uses. So when you just discharge a capacitor, and you can flip a bit in one direction if it's from 0.
Your example where you're saying we're assuming one is charged, what would happen is it would flip from 0 to 1, one of the ones would flip.
Correct, correct. So I'm here, it's an inconsistency of the slides. But yes, you can flip it both ways in practice. Although we actually have some numbers as to what we found, actually. It turns out that one direction tends to be a lot more prevalent than the other, and we don't really understand why. Yes? So, oh, yeah, to many more. So here in this example, I'm showing you're flipping 1. You might flip more than 1, although most of the time you flip none. Okay, so that's how you should think about it. Like one flip, it's pretty good. Flipping more than 1, you have to hammer a lot. The thing that when you hammer, so remember that every 64 milliseconds, row number 2 is being refreshed. And when it's refreshed, you undo all that leakage you've done. So you want to hammer fast enough that within 1 nanometer interval, you can cause 1 bit flip. Once you close the bit flip, the refresh will persist that, will keep that around. But if you haven't flipped a bit yet, all the work you've done in creating noise on that circuit is undone. Okay? Okay. Yes, sorry. Yes?
So do you get to control which bits you flip, or is it just probabilistically I'm going to mess something up?
Yeah, it's probabilistic. It has to do with weak DRAM cells, whatever that means. In general, when you start flipping some bits, those bits tend to flip consistently, more consistently. But it's a probabilistic event or phenomenon. It's not. Yes?
The mic's not working.
I don't know, I'm not doing anything.
Change the battery.
Okay, how about now?
Yeah, the fact that you don't know, that's why people want to reverse engineer the mapping between the memory controller and so if that was public information, this could be a little easier to do.
Yeah, I'll get to that quite a bit. That's the second part of my talk. Okay, so let me go to how we build this DRAM testing methodology and what are its requirements. So before I do that, I want to tell you about these papers. I told you there are a lot of papers. They use proofs of concept. What does that mean? A proof of concept follows this two-step sort of recipe. The first step is I'm going to use some sort of instruction sequence. I'm going to run a little bit of a small program that's going to generate a rate of row activations that's high enough to flip some DRAM cells on a particular DIMM that I found. Okay? And once I found this sort of setup, Then the second step is, let me find the bit that's important to security, place it in that weak DRAM cells, and flip it, okay? And most bits in memory, you don't want to flip them. But most bits in memory, if you flip them, nothing really bad security-wise happens. But definitely there are bits out there that are really important for security. So for example, page tables in your operating system, you have page table entries that keep track about what permissions you have over these page tables. And those are bits. You flip one of those bits, suddenly your permission changes about your page tables, and that's bad. Now, this two-step approach of mounting a proof of concept attack is unsuitable for testing. On our memory, you run these previous instruction sequences, and they don't flip any bits. And you can say, oh, it's safe. But you just don't know if it's safe or not. The fact that you haven't observed bits, you don't know whether you actually created the worst-case scenario for that memory. And here on this slide, I'm going through some logical philosophy argument that where if you look at the phenomenon and you don't see it, doesn't mean it doesn't exist. And I'm just going to skip that because I think you guys understand that problem. If you look at these papers, there are many questions left unanswered. And here are some of these questions. People use their favorite instruction sequence. How effective are these instruction sequences? How fast are they hammering memory? And the second question is, how far from the optimal we are? How fast? Yeah. So how, you know, when you have this instruction sequence, one is faster than the other one, but how far from the optimal are you? You know, what's the optimal way to really hammer memory? Second question, some attacks never, some rows never flip any bits. Why is that? Is it because you're not hammering, is it because you're not adjacent to them when you're hammering, or are they somehow more resilient in some way? Actually, I'm going to show you some results there too. What configuration changes were made to the server used to actually flip bits? Turns out that there are a lot of changes you can make to the server. They're kind of useful to make your attack easier to mount in practice, but not realistic. One change is you can change the refresh interval. Some of the biases allow you to do that. You say, the memory controller is not going to issue enough refreshes every 64 milliseconds. Instead, I'm going to increase my refresh interval by a factor of 10. And by doing that, your memory becomes more attackable. But from a cloud provider point of view, that's not interesting because nobody operates the memory in a regime it's not supposed to operate it under. So yeah, it's not interesting that way. And the last question is, how difficult is to place a security critical bit in that particular location? And to be fair, people have started looking over this question now, if you'll actually read the more recent papers as to how many bits there are important security-wise. So they're starting to work on these questions. Okay, for our work, we're going to assume a worst-case threat model. We're going to assume that the attacker knows the instruction sequences that hammers memory optimally. It's going to have perfect knowledge of how the rows are adjacent inside of the chips. And I'm going to show you how that's very difficult, but we're going to assume that's possible. It's going to know what the configurations are on the servers. And we're going to assume that any flip bit is a risk. Okay?
It shut off.
Next time, so I forgot sometimes. This is definitely.
Is it just out of battery? I don't know.
It kind of, okay. Okay? Okay, so to build such a testing methodology, you need to have at least the following two requirements in practice. You have to create worst-case conditions. So you have to find an instruction sequence that generates the highest rate of activations on a server. And you have to hammer rows that are adjacent inside of the DRAM device. And this is hard. Let me tell you why this is hard. Well, so what are the challenges of generating the highest rate of activations? First of all, how do you measure this rate of activations? There is no way in software that you can say, I want to measure how fast my memory activates. You just don't know. And also, the effectiveness of instruction sequence varies. Instructions are executed out of order all the time. The CPU is built to really maximize the hit rate of the caches. So it's going to rearrange your instructions to make sure you always go to cache. When in fact, from an attack point of view, you don't want that. You want to go to the memory. The second problem, how do you hammer rows whose cells are adjacent inside of the DRAM device? So now I'm going to go after this, and I'm going to show you a picture. Here you have 3 maps of how rows map all the way to the DRAM device. Here, you have virtual addresses. Because when you run a program, that program uses virtual addresses. Those virtual addresses map to a set of physical addresses. That map is maintained by your operating system or your hypervisor. you might have one map, or if it's a hypervisor, you might have many such maps, because hypervisor also have sort of nested maps inside of them. But let's say you figured that out, okay? So this is the, I'm jumping, so this is the first map. And I'm saying here OSs are designed to scatter virtual memory across physical addresses, blah, blah, blah. Let's say you know that map. The next map is maintained by the memory controller. That's a map from physical addresses to bus addresses. I want to talk to DIMM 0, bank 3, row 1, column 1. These maps are underspecified, and they change from one CPU architecture to another, and they're subject to the configuration of your BIOS. And I don't have time to go over that, but they're quite complicated. You need to reverse engineer them. But even if you do that, there is this last map, which is internal to the DRAM. The fact that memory controller says I want to row 1 and then row 2, the DIMM doesn't need to make sure that 1 and 2 are next to each other. That's not part of the convention. The DIMM is free to actually put 1 there and 2 somewhere else. And in fact, memory vendors do that all the time. Okay? So those are challenges. So now let me tell you how we accomplish challenge number 1, requirement number 1, instruction sequence that hammers memory optimally. So here's what we're going to do here. I'm going to show you how the current instruction sequences that people use, how they hammer, and I'm going to show you a sequence that hammers DRAM on Skylake optimally. This sequence is not yet published, okay? So you are part of the first people who learned about this sequence. Okay, so how do we measure activation rates? We bought hardware. This is a bus monitor that interposes on your bus from the memory controller to the DIMMs, and it has 2 components. It has an FPGA here, and it has a memory interposer. And what you do is you insert that device. Here I have a diagram in your cloud server that has CPUs and memory. And this device, actually, you run an instruction sequence here that's going to trigger some trace being collected on your bus, and you're going to export that trace, and you're going to analyze it, okay? So what we did was we went over the many dozens of papers, and we collected all the Rowhammer instruction sequences that we found, and we also came up with new ones. And what I'm showing here is a template of how many of these instruction sequences look like. What they have is they have 2 load instructions, and in Intel that's move instructions. They have 2 CL flushes, and because the CPU reorders things to actually take advantage of the cache, some instruction sequences use fences. Fences guarantee that things are actually not executed out of order. And Intel supports 3 types of fences: a load fence, a read fence, a store fence, a write fence, an end fence that's global. The 4th type is, let's say I'm not using a fence at all. Some instruction sequences don't bother using fences. The first paper, Rowhammer, used the end fence instruction sequence. Now, what's the activation rate for these instruction sequences? So before I show you the data, let me show you the graph so that it makes sense. On the x-axis, I'm counting the rate of activations. And that's the number of activations per TREF. TREF is a DRAM timing parameter that is the distance between 2 refresh commands. Remember, there are 8,000 of them in 64 milliseconds. Don't worry what it is, kind of like a unit of time. So this is, in some sense, a rate of activations. And the y-axis, I have a CDF. And I know my memory from the specification can go all the way up to 167 activations per TREF. So what is the activation rate for the first instruction sequence we tested, the one with the M-fence? It's about 33% from what the memory can do. So what's interesting here is that even if you have there's DRAM out there, and even if you hammer it 33% from what the memory can do, can still cause bits to flip. So that particular memory is pretty bad. Okay, so we're quite far from that. Why are we so far from that? So now I'm going to show you a different graph. This graph changes the x-axis. This is the distance between 2 activates. And I know that the memory can do a distance of about 47 nanoseconds between 2 activates. And half of my activates go back to back every 47 nanoseconds. But the other half go very far, 220, 230 nanoseconds. So here's why. So here I'm showing you sort of an illustration of how the trace looks like. The trace looks like I get 2 activates back to back, then nothing for a while. Then 2 activates back to back, then nothing for a while. So what's happening is, because I'm using a fence, those two activates, those two reads go back to back, then the next time I'm going around the loop, that fence slows me down. And one of the results this actually we found, and I'm going to show you more data, fences are super slow. They slow you down quite a bit. Don't use fences. The problem is when you don't use fences, the CPU is going to reorganize things to hit the cache. That's also bad. So you're kind of stuck between these two things. Now let me show you more data. These are all the instruction sequences, the 4 of 1, M fence, L fence, S fence, no fence. And what you can see here is that the most effective ones are the ones that impose no ordering, either no fence, the one in the yellow, or right fence. A right fence imposes no ordering because there is no writes I'm doing in this instruction sequence. And in fact, for Skylake, for the particular, we found that in Skylake, when you use S fence, it's actually a little bit faster than no fence at all. People say, but why is that? I can't tell you why that is. It just, we sort of saw that S fence actually makes things a little faster. This distance is very small here, by the way. However, we're halfway there. The memory can do twice more than actually these instruction sequences can do. And then people say at this point, oh, but maybe you should change your instruction sequence in some other way. So for example, there's this new instruction sequence called CL flash optimized for Skylake, which is a linear one. Maybe you should use that instead of CL flashes. Or maybe you want to use non-temporal reads, which bypass the cache, because that's better. Or mark memory pages uncacheable. We've collected all these suggestions people have made, and we came up with a set of 42 different instruction sequences, and we measured them all. And I don't have time to tell you about the results. These things actually don't make things any faster, but the thing that makes things faster is using CL flash opt. These graphs shows the same 4 instruction sequences as before, but I'm replacing the CL flash with the CL flash opt instruction sequence. And what you can see here is that using CL flash opt makes things a little bit better. It moves the curves to the right. And the curve that's the best is the one that uses no fences. Fences are slow, but we're still about 2/3 of the way there. So the takeaway point from this graph is that today, as far as I can tell, nobody hammers their memory optimally. The memory can be hammered a lot harder than it actually becomes today. Yes?
Maybe it's too complicated, but why bother using a computer? Why not like get fancy hardware?
Yes, that's a great question. That's a great question. And people have done that. Another thing you can do is you can take your DIMMs and attach an FPGA to them and then hammer them and you write your favorite sort of protocol. And doing that, you can hammer it much faster than the memory is supposed to, and you're going to flip bits. The reason I'm coming from the perspective of the cloud. In the cloud, the attacker has a lot of freedom to do. It can run things, but it won't take the DIMMs out and attack them that way. So that's why I also I want to do my stuff in my server as much as possible. Okay. Yeah, I told you memory variants are slow. In the absence of memory variants, the CPU reorders. So what I wanted to show you here is that this instruction sequence is slow, but whenever we run things, we never serve them from the cache. This is faster, but 33% of my access come from the cache rather than from memory. This is, I have to press this button and
There's another mic under the table there.
Ah, yes, there is, you're right. Okay. Okay, so let me move on. Now, so it turns out that we actually found a sequence that hammers memory optimally. What is that sequence? So let me tell you a little bit of the intuition we had here. We said, well, we need an instruction sequence for which there are no memory barriers, because we know those are slow, and it's somehow less prone to the CPU reordering effects. So we thought to ourselves, maybe we should issue a lot of instructions that fill the CPU pipeline with all sorts of random instructions that don't do anything. And one of the things we tried was this instruction sequence, where we have 2 loops. We have an outer loop with 2 loads, and then rather than having just 2 CL flash opt instructions, we have an inner loop of them. We have many of them, because that doesn't do anything anymore if we execute more of them. And it's going to overwhelm, and every time I go through one outer loop iteration, even if this thing gets reordered here, that's okay, because the other things don't matter. It's not important. Actually, this instruction sequence is not important. What's important is that we found something surprising, which was flash instruction cause memory accesses. So on the next slide, I'm going to show you the instruction sequence that hammers memory optimally. It's that. You don't do any loads. You just do 2 CL flash ops in a loop. And this hammers memory amazingly well. So let me show you the graph of act-to-act latency. 95% of the acts are sent back-to-back at optimal rates, and 5% are a little slower. Why is 5% slower? Well, remember that the memory controller issues these refreshes every once in a while, and whenever a refresh happens, you're stuck behind that. And in fact, it uses a refresh every refresh interval. So if you look at the T-refi thing, my rate every interval is not optimal, because every interval I have to do a little bit of refresh. But that's pretty much the best I can do in practice, okay? So we hammer at about 159 activations per T-refi, where the optimal is 167. Why is CL flash op accessing memory? And we have a whole bunch of hypotheses. The first hypothesis was, well, CL flash op needs to evict the line and write it back, and maybe that's what's going on. That's not what's going on, because the lines are not dirty, there is nothing in the cache, and we see reads on the wire, not writes, so that's not what's going on. Then we thought maybe the memory prefetcher goes and prefetches the lines back into the cache. If you actually read the Intel manual, it tells you that during a CL flash operation, the prefetcher can go and grab back those lines and put them back in the cache. There are no guarantees that the lines are not in the cache. We ran an instruction sequence where we definitely concluded that's not the case. What we did was, if the memory prefetcher brings them back in the cache, then I should hit them in the cache next time I access them. And we tried a lot of things, and the lines were not in the cache. So probably it's not the prefetcher. It turns out that the CL flash opt, what happens is, when the line is in the cache, it was not going to generate this read. It's going to just invalidate the line. If the line is not in the cache, it says, oh my God, let me read the line back into the, let me read the line. And when I read that line, I get information about my cache coherency protocol, about the L3 across my system. And that's why Intel actually decided it's a good idea when the line is not in the cache to read the line, to read the line from memory. Okay? So that's kind of what's going on. To CL flash opt, that's how you hammer memory perfectly on Skylake. Okay, next requirement. We need to understand row adjacency. And to do that, we build a fault injector. So let me explain a little bit what we did here. How do we learn row adjacency inside of the DRAM chips? Well, you need this fine-grained way of doing that. So the way to do that, the way people know how to do that is to mount Rowhammer and flip bits. Because if I hammer this row, and I flip a lot of bits, I can look at where the bits that I flip are, and that tells me something about the layout of the bits in the real world. So that works great. Except that for us, we have this problem where it works as long as the DIMMs succumb to Rowhammer, and our DIMMs don't succumb to Rowhammer. So if you hammer them optimally, but they don't flip any bits, is it because the DIMMs are resilient, or maybe you are not flipping adjacency, and you cannot reverse engineer adjacency. So we have this chicken and egg problem. So what we actually thought was to build a device that suppresses refreshes, and we did the fault injector to do that. So here is the observation. We thought to ourselves that what we're going to do is, sorry, let me take this. So DDR commands are encoded using a set of electrical signals, right? So there are signals over the wire from the memory controller going to the DIMM. And we thought that what we should do is we should intercept these signals, decode them, and if it's a refresh, to suppress that refresh. Why do we want to suppress refreshes? If we suppress refreshes, then I can hammer my memory for many, many seconds, for a huge period of time, and I'm going to flip a lot of bits. And I'm going to guarantee that by doing that, I'm going to reverse engineer the adjacency no matter what. That's in some sense what somebody there saying, which was build your own thing that actually can mount this Rowhammer in practice. So we thought, okay, let's interpose on these signals, decode them, and to the refresh, drop it. You can't do that in practice, and I can explain to you a little bit why that's very difficult to do in practice. So instead, we had this other observation. Maybe we interpose on the signals and flip them. So what we want is, we want to find a signal that when I flip it, when I change the signal, I'm going to suppress my refresh command, but I still want to mount Rowhammer. So I need my activates, I need my precharges, and I need reads or writes, because that's how I mount Rowhammer. Okay, so then we looked over the table of how DDR4 works. And what you see on this table is DDR4 commands here, activate, read, write, pre-charge all banks, pre-charge one bank, refresh, and then a set of signals. And the way to read this is that if this signal is low, and this is high, and this is low, and this is low, and this is high, that's a refresh command. That's how the DIMM memory controller creates that signaling over the wires, and how does the DIMM decodes them. So I want to find a signal here to flip. So let's try to flip that one. When I flip this one, it means that the DIMM will always receive this signal as high. And that's bad. The reason why that's bad is because I lose all these other commands, because all of them are going to be flipped to high. So all of them will be interpreted as deselect. So when I flip this signal, all commands that the memory controller sends are going to be received as deselect. So I don't do anything useful. Does that make sense? And then I looked at the other. I don't have time for that. And we found one, A14. If I flip this to low, a refresh is going to become a mode register command, which is a configuration command. However, the pre-charges, if I put this to low, they're going to be received as before, because they have low, but that's nice. The activate doesn't use this bit. Great. So I can make that low too. Reads, unfortunately, I don't have anymore. I lose them, because the reads have high here. But I have writes, and I can all Rowhammer with writes. And that's how we did. Yes? I can depress the refresh command because I can control the memory controller. Memory controller, you turn power on, the memory controller starts sending refresh commands. It's a black box. I'm interposing on the bus between the CPU and the DIMMs. I'll show you a picture. And that bus receives these electrical signals as wires, and one of the wires, I'm short-circuiting it. So let me show you how that device looks like. Okay, so we found this A14. This is the first device we built. This doesn't work. This is an interposer. You plug this into your slot, and you plug your DIMM on top of it. And when you press that button, the A14 signals get short-circuited. And that makes sure that refreshes are not being received. Why doesn't this work? This doesn't work because the refreshes get changed to that MRS, that configuration command. And that configuration command unfortunately has side effects. And those side effects put the DIMM in a bad state. And we found a second signal that we also interpose on. And if we flip those two signals, so this is the A14 signal. These are a set of dip switches. Two of them, when you set them out, you flip this other signal that I'm not telling you what it's about. I'm happy to talk to you if you're interested. The third switch doesn't do anything. We just added a spare switch. This is the fault injector. And this is the setup we used in practice. So let me show you what this is. These are fault injector here. This goes into the slot. This is the bus monitor. So here we see all the commands that this spews out. And we want to interpose there because we want to check we see no refreshes. Because the refreshes come here, they get swapped to the MRS commands. And we validated that. And on top, we have our favorite DIMM. Okay? Does that make sense? Okay. And using that concoction, we can reverse engineer adjacency in any DIMM out there. And I'm going to show you the results from, let me just go over this because it's important actually, but I can skip it. We have a whole bunch of questions. So I'm going to show you some results from vendor number 1. It's one of the 3 vendors I mentioned before. So what I have here is the following experiment. I have a whole bunch of rows. I know these rows are consecutive in the logical space. Memory controller says row 411, 412, 413, but I don't know if they're consecutive, they're adjacent in the actual device. And what I'm doing is I'm hammering row 411, and I'm measuring how many bits flip on other rows. This y-axis is a log scale. What this means is that these bars are way bigger than these bars. So when I hammer 411, I see 50,000 bits on 410 and 50,000 bits on 412 flipping. They are adjacent. They have to be adjacent. Nice. Okay, so that means 1 to 1. 4110, 411, and 412 are next to each other. Next graph, I'm hammering 410. When I'm hammering 410, I see 50,000 bits on 411. Well, not surprising because I know 411 is adjacent. But then I see 26,000 bits on 40F. And then somewhere here on another row, I see another 26,000 or 24,000. So what's going on actually is that some of these rows are fully adjacent and some are half adjacent. They're adjacent with one row for half its length and with another row for another half. This is another picture of a portion of this particular DIMM. And what you see here is the adjacency map for row 08, 09, 08, 0B, and so on. And we hammer this, and we look at 75% of the bits flip on 409. So this is fully adjacent. Only 40% on 7 and 417. So 408 is fully adjacent with 409 and half adjacent with 407 and 417. But then these are fully adjacent again, and again half adjacency, and again full adjacency. Half adjacency is great. It's actually a lot harder to Rowhammer half adjacency. If you want to keep your data safer, put it in half adjacent rows. They'll be harder to Rowhammer. Sort of interesting. I don't have time to present all the results, and I don't want to go beyond my allocated time. These are sort of some of the results, and I'm happy to talk to you about. The takeaways are, logical rows do not always map linearly inside of this. And we checked DIMMs from all the 3 vendors, and they all use this half-row adjacency stuff. When you have a whole row, you can flip a lot of different bits. All bits are sort of equally susceptible, more or less. In half rows, some of the bits are equally susceptible, but some are not. And I can tell you a little bit more about that. It turns out that in half rows, you can flip bits depending on how the half row is laid out. You can either flip the most significant bits, the first 32 bits, or the last 32 bits. Not the last, but the most significant or the least significant, depending on how the row is laid out, which is very, very interesting. Most bits flip from 1 to 0, not from 0 to 1. We can't really explain what that is, but we found that to be universal. The maps differ from one vendor to another. And the other interesting stuff is that DIMMs sourced from different vendors have very different number of bit flips. Some are actually flip a lot fewer bits than others. They all have this adjacency phenomenon, but they all have different number of bits. And I'm going to stop now. Oh, this work has limitation. It's not perfect. I don't want to sell it to you as perfect. We can't really scale very easily because using this fault injector involves people pressing buttons, and that doesn't scale. We did all our work on Intel. We don't know how to actually, we can't tell you anything about ARM or AMD. Then are the other questions we haven't answered. So to wrap up, we developed an end-to-end methodology to test any cloud server. And I showed you 3 findings. All previous sequences have suboptimal activation rates. On Skylake, you want to see CL flash opts in a loop. That's the perfect way to hammer. And logical rows do not always map linearly inside of the DRAM devices. And that's my last slide. This is Owner from ETH. These are his 2 students who started working on this project. This is Lucian, who has the hardware skills that I don't have to build all those concoctions. Lily was a student working with us this summer, and she helped trying to run some experiments as to why is CL flash opt hitting the memory. And Alex is my collaborator. Thank you for your time. I'm happy to take more questions.